Hello friends, today we are going to start a series of lectures on network analysis. In the first lecture, which of course will be introductory, we shall be talking about the AC circuit analysis in which time varying electrical signals, particularly the sine wave, are studied. An electrical signal is a voltage or current that changes in some consistent manner with time. In other words, the voltage or current fluctuates according to a certain pattern called a waveform. An alternating voltage is one that changes polarity at a certain rate, and an alternating current is one that changes direction at a certain rate. The sinusoidal waveform, or more commonly known as sine wave, is the most common and fundamental type because all other types of repetitive waveforms can be broken down into composite sine waves. The sine wave is a periodic type of waveform that repeats at fixed intervals. Special emphasis is given to the sinusoidal waveform because of its fundamental importance in AC circuit analysis. Other types of waveforms are also introduced, including pulse, triangular, and sawtooth. After completing this lecture, you should be able to identify a sinusoidal waveform and measure its characteristics, determine the period and the frequency, relate period and frequency, describe how sine waves are generated, discuss the basic operation of an AC generator, talk about factors that affect frequency in AC generators, and finally, discuss factors that affect voltage in AC generators. The sinusoidal waveform. The sinusoidal waveform or sine wave is the fundamental type of alternating current and alternating voltage. It is also referred to as sinusoidal wave or simply a sinusoid. The electrical service provided by the power company is in the form of sinusoidal voltage and current. In addition, other types of repetitive waveforms are composites of many individual sine waves called harmonics. Sinusoidal voltages are produced by two types of sources: rotating electrical machines, commonly called the AC generators, or electronic oscillator circuits, which are used in instruments commonly known as electrical signal generators. Figure here shows the symbol used to represent either source of sinusoidal voltage. This figure here is a graph showing the general shape of a sine wave, which can be either an alternating current or an alternating voltage. Voltage or current is displayed on the vertical axis and time is displayed on the horizontal axis. Notice how the voltage or current varies with time. Starting at 0, the voltage or current increases to a positive maximum, returns to 0, and then increases to a negative maximum before returning again to 0, thus completing one full cycle. Polarity of a sine wave. As just discussed, a sine wave changes polarity at its 0 value, that is, it alternates between positive and negative values. As shown in this figure, when a sinusoidal voltage source Vs is applied to a resistive circuit, an alternating sinusoidal current results. When the voltage changes polarity, the current correspondingly changes direction as indicated. During the positive alternation of the applied voltage Vs, the current is in the direction shown in figure. During a negative alternation of the applied voltage, the current is in the opposite direction. The combined positive and negative alternations make up one cycle of a sine wave. Period of a sine wave. A sine wave varies with time in a definable manner. The time required for a sine wave to complete one full cycle is called the period. Figure here illustrates the period of a sine wave. Typically, a sine wave continues to repeat itself in identical cycles as shown in part B. Since all cycles of a repetitive sine wave are the same, the period is always a fixed value for a given sine wave. The period of a sine wave can be measured from a zero crossing to the next corresponding zero crossing. The period can also be measured from any peak in a given cycle to the corresponding peak in the next cycle. There are three possible ways to measure the period of a sine wave. Method 1. The period can be measured from one crossing to the corresponding zero crossing in the next cycle. The slope must be the same as the corresponding zero crossings. Method 2. The period can be measured from the positive peak in one cycle to the positive peak in the next cycle. Method 3. The period can be measured from the negative peak in one cycle to the negative peak in the next cycle. Here we are to keep in mind that we obtain the same value for the period no matter which corresponding points on the waveform we use. Frequency of a sine wave. The frequency is the number of cycles that a sine wave completes in 1 second. The more cycles completed in 1 second, the higher the frequency. Frequency is measured in units of hertz. For example, 1 hertz is equivalent to 1 cycle per second. 60 hertz is 60 cycles per second. Figure shows two sine waves. The sine wave in part A completes 2 full cycles in 1 second. The one in part B completes 4 cycles in 1 second. Therefore, the sine wave in part B has twice the frequency of the one in part A. Hertz, a German physicist, was the first to broadcast and receive electromagnetic or radio waves. He produced electromagnetic waves in the laboratory and measured their parameters. Hertz also proved that the nature of the reflection and refraction of electromagnetic waves was the same as that of light. The unit of frequency is named in his honor as Hertz. Relationship of frequency and period. The formulas for the relationship between frequency f and the period t are as follows. Frequency is equal to 1 upon t and time is equal to 1 upon f. There is a reciprocal relationship between f and t. Knowing one, you can calculate the other with x to the power minus 1 or 1 by x key on your calculator. The inverse relationship makes sense because a sine wave with a longer period goes through fewer cycles in 1 second than one with a shorter period. Sinusoidal voltage sources. Two basic methods of generating sinusoidal voltages are electromagnetic and electronic. Sine waves are produced electromagnetically by AC generators and electronically by oscillator circuits. Figure shows a greatly simplified AC generator consisting of a single loop of wire in a permanent magnetic field. Notice that each end of the wire loop is connected to a separate solid conductive ring called a slip ring. A mechanical drive such as a motor turns the shaft to which the wire loop is connected. As the wire loop rotates in the magnetic field between the north and south poles, the slip rings also rotate and rub against the brushes that connect the loop to an external load. You must have learned that when a conductor moves through a magnetic field, a voltage is induced. Figure here illustrates how a sinusoidal voltage is produced by the basic AC generator as the wire loop rotates. An oscilloscope is used to display the voltage waveform. To begin, figure A shows the wire loop rotating through the first quarter of a revolution. It goes from an instantaneous horizontal position where the induced voltage is 0 to an instantaneous vertical position where the induced voltage is maximum. At the horizontal position, the loop is instantaneously moving parallel with the flux lines which exist between the north and the south poles of the magnet. Thus, no lines are being cut and the voltage is 0. As the wire loop rotates through the first quarter cycle, it cuts through the flux lines at an increasing rate until it is instantaneously moving perpendicular to the flux lines at the vertical position and cutting through them at a maximum rate. Thus, the induced voltage increases from 0 to a peak during the quarter cycle. As shown on the display in part A, this part of rotation produces the first quarter of the sine wave cycle as the voltage builds up from 0 to its positive maximum. Figure B shows the loop completing the first half of a revolution. During this part of the rotation, the voltage decreases from its positive maximum back to 0 as the rate at which the loop cuts through the flux lines decreases. During the second half of the revolution illustrated in figures C and D, the loop is cutting through the magnetic field in the opposite direction. So, the voltage produced has a polarity opposite to the produced during the first half of the revolution. After one complete revolution of the loop, one full cycle of the sinusoidal voltage has been produced. As the wire loop continues to rotate, repetitive cycles of the sine wave are generated. Frequency. You have seen that one revolution of the conductor through the magnetic field in the basic AC generator, also called an alternator, produces one cycle of induced sinusoidal voltage. It is obvious that the rate at which the conductor is rotated determines the time for completion of one cycle. For example, if the conductor completes 60 revolutions in 1 second, the period of the resulting sine wave is 1 upon 60 seconds, corresponding to a frequency of 60 hertz. Thus, the faster the conductor rotates, the higher the resulting frequency of the induced voltage, as illustrated in figure. Another way of achieving a higher frequency is to increase the number of magnetic poles. Here we have used two magnetic poles to illustrate the AC generator principle. During one revolution, the conductor passes under a north pole and a south pole, thus producing one cycle of a sine wave. When four magnetic poles are used instead of two, one cycle is generated during one half a revolution. This doubles the frequency for the same rate of rotation. The voltage induced in a conductor depends on the number of turns and the rate of change with respect to the magnetic field. Therefore, when the speed of rotation of the conductor is increased, not only the frequency of the induced voltage increases, so also does the amplitude, which is its maximum value. Since the frequency value normally is fixed, the most practical method of increasing the amount of induced voltage is to increase the number of wire loops. Electronic signal generators. The signal generator is an instrument that electronically produces sine waves for use in testing or controlling electronic circuits and systems. There are a variety of signal generators ranging from special purpose instruments that produce only one type of waveform in a limited frequency range to programmable instruments that produce a wide range of frequencies and a variety of waveforms. All signal generators consist basically of an oscillator, which is an electronic circuit that produces repetitive waves. All generators have controls for adjusting the amplitude and frequency. Function generators and arbitrary waveform generators. A function generator is an instrument that produces more than one type of waveform. It provides pulse waveforms as well as sine waves and triangular waves. A typical function generator is shown in figure. An arbitrary waveform generator can be used to generate standard signals like sine waves, triangular waves and pulses, as well as signals with various shapes and characteristics. Waveforms can be defined by mathematical or graphical input. A typical arbitrary waveform generator is shown in this figure. So friends, this brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we discussed that the sine wave is a time varying periodic waveform. Alternating current changes direction in response to change in the polarity of the source voltage. One cycle of an alternating sine wave consists of a positive alternation and a negative alternation. Two common sources of sine waves are the electromagnetic AC generator and the electronic oscillator circuit. A full cycle of sine wave is 360 degrees, a half cycle is 180 degrees and a quarter cycle is 90 degrees. So that is it for today. See you in the next lecture, and we shall be discussing about voltage and current values of sine wave and angular measurement of sine wave. Thank you very much.